Hi, in this video we're going to talk about visualizing numerical data, but before we dive into that, let's lay out our terminology a little bit. The number of variables involved in your data analysis will determine some of the terminology that we're going to use. For example, when we say univariate data analysis, we're talking about looking at the distribution of a single variable, which tends to not always be very exciting, but might be a good starting point for starting to learn about our data. Bivariate data analysis is when we're looking at the relationship between two variables, which is starting to get more interesting. But where things get actually interesting is when we're doing multivariate data analysis. So we're looking at the relationship between many variables at once. And usually the way we're going to do this is we're going to focus on the relationship between two while conditioning for others. The types of variables that we're going to talk about are numerical and categorical. So numerical variables can be classified as either continuous or discrete based on whether or not the variable can take on an infinite number of values or only non-negative whole numbers, respectively. So for example, if I was to ask you your age today, chances are you would give me a whole number. But truthfully, your age doesn't change in discrete scales. In fact, if you think back to your childhood, you probably said things like, I am 4.5 years old. I am 4 3/4 years old. So I think as children, we tend to be more excited about getting older. So we actually try to kind of establish those milestones along the way. As adults, we tend to kind of just round things off to a whole number. So when we think about what sort of numerical variable we're dealing with, continuous or discrete, it is not so much about how a human may have reported it on a survey, but more about how we expect that variable to be measured or to change from individual to individual. So for most purposes, we can think of age or height as continuous variables since they don't tend to change in discrete scales. But if you're talking about things like number of cats, number of dogs, how many cars you own, so things that you count, then we're talking about discrete numerical data. If the variable is categorical, then we can determine if it is ordinal or not based on whether or not the levels have a natural ordering. If you think about survey questions, for example, where you're asked to indicate on a scale from strongly disagree to strongly agree, and so it tends to be like strongly disagree, neutral, agree, strongly agree, there's an inherent ordering to those levels. So a categorical variable like that is one that we would say to be ordinal. Other categorical variables don't have an inherent ordering. So for example, sex does not have an inherent ordering, whatever anybody might tell you. And so we would not categorize that as an ordinal categorical variable. Ordinal variables are important to take note of because when we visualize those data, we want to make sure that we're representing the data in the order that it logically makes sense. The data set that we're going to be working with for this video, it comes from the Lending Club. So this is a peer-to-peer lending platform. So the data we have is from thousands of loans made through the Lending Club, which is a platform that allows individuals to lend to other individuals. If you know anything about loans, you know that not all loans are created equal. So ease of getting a loan depends on one's apparent ability to pay back the loan. And so the data set we're going to work with actually only includes loans that are made, not the loan application. So it's important to keep that in mind when we're looking at the relationships between the variables that we're going to see, since the pattern may be different for those relationships for loans that never got approved. Glimpsing at the data, we can see that we have 10,000 rows. So that is how many observations or how many loans we have in this data set, and 55 columns. The data come from the Open Intro package, so I loaded that first, and the name of the data frame is Loans Full Schema. So this result is basically the output of the glimpse function when I look at that data frame. 55 columns is a lot to kind of go through, so we're not going to go through each and every one of them, but you can basically see the types of variables that we have here. The variable names are somewhat kind of self-explanatory. But for this particular analysis, we're only going to focus on 8 of these columns: the loan amount, the interest rate, the term, grade, state, annual income, home ownership, and debt to income ratio. So what I've done is I've taken that loans full schema data frame and I've piped that into the select function, which allows me to select the variables that I want by name. And I'm going to select only these 8 variables. So when I look at output, like the glimpse output, I can actually see everything I need in one place. And I'm going to call that new data frame loans. So from now on, when I refer to a data frame called loans, I'm talking about a data frame that includes all of the loans from the original data set, but only 8 of the columns. Here is a data dictionary for these 8 columns. So the loan amount is the amount of the loan received in US dollars. The interest rate is the interest rate on the loan in an annual percentage. The term is the length of the loan, which is always set as a whole number of months. The grade is takes the values A through G and represents the quality of the loan and its likelihood of being repaid. The state is the US state where the borrower resides. Annual income is borrower's annual income. Home ownership indicates whether the borrower owns but has a mortgage or rents their residence. And debt to income ratio is, well, debt to income ratio. If you have more debt than your income, then that number should be above 100%. And if it's lower, then your income is higher than your debt. And here are the variable types. So loan amount, interest rate, and term are numerical variables. And so is annual income and debt to income ratio. And we can see that some of these are continuous. So for example, loan amount and interest rate are continuous, and so is annual income and debt to income ratio. But term, we were told, is always given to us in whole number of months. So that is a discrete variable. The grade of the loan is a categorical variable where the levels have inherent ordering. We said they went from A to G and that those levels mean something in order, versus the US state where the borrower resides is a categorical variable, but the levels are not ordinal. And similarly for home ownership, we had 3 levels: own, mortgage, or rent. And there we again have a categorical variable which is not ordinal. So for this video, we're going to focus on only the numerical data from the data set. And when we're working with numerical distributions, one of the things that we want to describe is the shape of the distribution. And oftentimes we talk about the skewness. So whether the distribution is right skewed, which would mean that there's a long tail on the right side, or left skewed, which would mean there's a long tail on the left side, or symmetric. And so in terms of the terminology, skew is always to the side of the longer tail, and symmetric distributions look like, if you were to put a line through them, both sides of them would be mirror images. We are often also interested in modality. So unimodal means we have 1 prominent peak, bimodal means we have 2 prominent peaks, and multimodal means we have multiple prominent peaks. Usually these modes are driven by various subgroups in your data that tend to share characteristics with each other but are different from the other subgroups. And a uniform distribution means we have no prominent peaks. The measures of center are things like the mean, the median, which is the midpoint of your data, the 50th percentile, or the mode, which is not always useful, especially when you have continuous data, because the definition of the mode is the most frequent. But when you have continuous data, there's not going to be as many repeated observations. The spread is measured by things like the range, which is just the difference between the minimum and the maximum, the standard deviation, which tells us about the variability around the mean, or the average variability around the mean, and the interquartile range, which is about the middle 50%. And another thing that we usually want to note is any unusual observations in our data. When I say we want to note, I don't mean we want to eliminate them. Sometimes those are the most interesting observations in your data. We just want to make a note of them and decide explicitly on how we want to handle them. One of the most commonly used ways of visualizing numerical data is with histograms, and we can create a histogram with ggplot2 using geom histogram. When you do this, and by default, ggplot is actually going to report this message to you, which says that it's using 30 bins, so it organizes your data into 30 bins or 30 columns here, and it asks you to pick a better value with bin width. So that is about being explicit about which bin width you want to use and how you want to organize, in this case, these loans. In this plot, I've used a bin width of $1,000. So each one of the bars represents a range of $1,000. And the heights of these bars tell me how many loans fall into that bin. In the second plot, I have used a bin width of 5,000. So here I have a better sense of the shape of the distribution, it seems like, while in the first one, everything was so jagged that it would have been hard for me to tell whether the distribution of loans is right skewed or left skewed or symmetric. And in the last plot, I've used a bin width of 20,000. So I've organized the loans into ranges of $20,000. And now I've really lost anything interesting about the shape of my distribution. So picking a bin width is an art and a science, I suppose. There is some subjectivity that goes into it. But I think a better way to think about it instead of subjectivity is maybe domain knowledge. So you might think about what amount would make sense to bin together. And I think we can all agree that binning at the dollar level, when you have loans ranging from $0 to $40,000, wouldn't make sense. So something on the order of thousands, a little bit more informative. And then once you make that decision, you want to start thinking about, is this too jagged for me to learn something useful from? Is there a higher number for the bins that I could use where I still get a sense of the shape of the distribution without losing anything that's interesting about the shape of my distribution? So I would say 5,000 looks good. And I can see based off of this that I have a right skewed distribution, which is expected, I think, because the larger the loan amount, the less likely that somebody's getting such a loan, especially from a peer-to-peer lending platform. We can also customize our histograms. By default, we don't get a title for our histogram, and the way our X and Y axes are axis labels are determined are simply based off of the way the variable names are represented in our data set. So here what I've done is I have changed the labels. I have given it an X label where I say it's the loan amount, and I also say the unit of the observation. Y, by default, ggplot2 uses the word count. I like using the word frequency. And then title is amount of lending club loans. I can also fill a histogram with a categorical variable. So this starts allowing me to explore relationships between numerical and categorical variables. So the way we have done this is by adding a new aesthetic called fill. So I'm saying now that you have these bars, fill it based on the home ownership variable. And so that I can actually see what's happening behind each level, I have changed the alpha level for the bins so that I can see a little bit better how each of these heights of each of the bins correspond to the y-axis. I can also facet with a categorical variable. So here I have done the filling in with the colors based on the home ownership level. But instead of changing the alpha level and putting them on top of each other, I've said I'd like to facet. And since I'm using a single variable to facet, I'm going to use the facet wrap function. So I want to facet wrap by the home ownership variable, and I want the data to be represented in 3 columns. The reason why I'm sorry, 3 rows. The reason why I use 3 rows is so that they could be on top of each other so that I can have a shared x-axis, which I think makes it easier to see what's happening with each one of these. They each have the same y-axis scale. So I can see, for example, that home owners are the least represented in this data set in terms of people who are borrowing money. But those who own a home but have a mortgage on it, or those who are renting, seem to be roughly, the representation of them in the data seems roughly similar. And we also see that for each one of these types, we have a right skewed distribution for the loan amount. Another way we can visualize numerical data is using a density plot. So I always think about density plots as, what if I was to fit a smooth curve on my histogram? And what I mean by that is, imagine that your histogram was made of wooden blocks, and you took a limp piece of spaghetti, say one you just boiled and took out of the pot, and dropped it over these wooden blocks. It would kind of drape itself. And that draped look is basically what a smooth curve looks like. So we create a density plot in ggplot2 using geom density. And by default, it picks a level of smoothness. And we can see that in this particular plot, that smoothness is not very smooth. It looks a little bit jagged, the line, like things look jagged when we had a low bin width for our histogram. So we can do some adjustment with this as well. So we can adjust the bandwidth that is being used for the geom density layer. So if I adjust it to 0.5, that's actually making the bandwidth even smaller than half as big as the default. So I'm going to get something that's a lot more jagged. Adjust equals once is basically the default, what we got before. And adjust a larger number is basically expanding that bandwidth where the smoothing is being done. So by increasing this number, we can get a smoother and smoother curve. This looks somewhat okay to me, but I'd probably play around a little bit more around the value too, to see if there's something that maybe gives me, if there's any other feature that I want to capture, that it gives me that as well. The higher this number is, the more likely you're going to lose any sort of local maxima, for example. But I think we saw earlier in our histogram that we liked with the bin width of 5,000 that there wasn't really such a feature. So this looks pretty good. We can similarly customize density plot. So here I've basically changed the labels for X and Y and the title to again make it a little bit more informative, but I haven't played around with it any further here. I can also add a categorical variable. So this is similar to what we did with the histograms, where you could see them overlaid on top of each other. But instead, we're just doing it with a density plot. So once again, I'm filling in the curves based on the value of the home ownership variable. I am changing their alpha so that we can actually see what's happening behind the curve. So here, especially if I didn't change the alpha, this rent would kind of cover up what's happening in terms of the peaks of own and mortgage. So with the alpha level being set to a number less than 1, I can see that. And I also adjusted the name of the legend to home ownership with a capital H. Another way of visualizing numerical data is using box plots. So here I have a box plot of the annual income, and I've purposefully chosen this one instead of the loan amount because one of the things that box plots are really good at uncovering are potential outliers, and income tends to be highly right skewed in the US, really in any country, but especially in the US. And so we have some people who are making a lot higher income than others, but those are far and few between, versus a lot of the people kind of make around the median income. So we can see over here that majority of our data is like kind of squished at the lower end, but we have this really, really high tail, and we can identify some of our extreme outliers. For this, we use the geom box plot function in R. Here's another one. This is a box plot of the interest rate. And again, we can see the outliers here as well. Some people are getting loans with a lot higher interest rate than others. We can also customize our box plots as well. And one of the things that we might want to customize is what's actually happening on the y-axis. So if we actually took a look, say, at this one with annual income, you can see that on the y-axis, I have something like values ranging from negative 0.4 to positive 0.4, but these are not really meaningful values. They're just about the width of this box, or the height of this box, really, that's not informative to us. It's the width of it that gives us the inner quartile range that we're actually interested in. So those are there by default in ggplot2, but they're not informative. So I like taking those out, which means further customization of the plot axes beyond just touching the labels. So here I need to go into the theme level. So remember the levels in which we were building the visualization. So this is something that happens at the theme level. And I say for the ticks and the text of the y-axis, just make them blank. So the function we use for that is element blank. This is very ggplot2 specific syntax. It is a little bit harder, in my opinion, to read and make sense of. So it does take a little bit of getting used to. And the nice thing is, out of the box, ggplot2 visualizations are pretty good. So rarely do you have to touch and fiddle with these things, but every once in a while I think it helps to do so. So here I have removed the ticks and the text for the y-axis, and I've done that in an additional theme layer. I can also add a categorical variable to a box plot. So these are called side-by-side box plots, and they're very commonly used. So we can see that the interest, this is the distribution of the interest rates of lending club loans by the grade of loan. We had said that the grade varies from A to G, and that was something about the quality of the loan. So it looks like the higher the quality of the loan, so the more likely that it's going to be repaid, we would anticipate the lower the interest rate, because it presents less of a risk to the lender. And those are labeled grade A, versus once we get to grade G, we're seeing that the interest rates are a lot higher. So to create this visualization, you can actually add a variable to the y-axis of your plot. And I've also added a subtitle just to indicate what this is, what the plot is actually showing us. In order to explore relationships between numerical variables, we've talked about scatter plots before. So here I have a scatter plot of the interest rate and the debt to income ratio. So think about this as if you have higher debt to income ratio, chances are you are maybe slightly riskier, maybe not. It's a little bit hard to tell what's going on over here. And especially for these people where their debt to income ratio is above 100%, there are very few of them. And it seems like something special might be going on about them. So what I'm going to do is I'm going to first bin these data. So instead of using geom point, I'm using geom hex now, which is basically going to kind of group together data within certain areas that are in my plot, and the color of these hexes is what tells me how dense my data are. So the lighter the color, the more data points I have there, and this is a useful visualization for when you have a large number of data points, which we do, 10,000 of them, and there's so much overplotting happening here that it's really difficult to make sense of the scatter plot that we built with geom point, that the geom hex comes in handy. I'm going to do one more thing here where I change the data set that I'm plotting a little bit. I'm going to filter these to just the people whose debt to income ratio is less than 100%, because it seems like I have a better sense of what's happening with them than people who had a lot more debt than income. And so we can do this directly in the ggplot call. I would only recommend doing this sort of stuff if the adjustment you're making to the data frame is very simple, like this one here, for a quick look. And so now what we can see is that around the 12%, I guess this is about 12% debt to income ratio, or somewhere between 12.5 to 25, we're seeing a lot more loans being made at that level compared to other areas, where as the debt to income ratio increases, the hexagons are getting darker and darker, which basically tells me that fewer and fewer loans being made there. And then also very few when your debt to income ratio is 0. And this might be because if you have no debt whatsoever, you have no credit history whatsoever. So it might be difficult for the lender to judge your riskiness level.